Hello, my name is Dr. Gulshan Sharma. I'm a pulmonary critical care physician by training, and I serve as the Chief Medical Officer of the University of Texas Medical Branch. We at UTMB Health are very pleased to once again be with you for another inspirational evening of listening and learning from the Space Center Houston. It is our pleasure to help bring you the Thought Leader series we have enjoyed being part of every session this past year. It's been a challenging year for all of us, one of change, adjustment, accommodation, and vigilance. In the health field and in my role at UTMB, we have worked hard to monitor and stay ahead of the ebbs and flows of COVID in our communities. We have worked to keep our employees and students safe, as well as provide excellent care for our patients who were hospitalized during that time. We are now in the holiday season, and we all are so starved for the love and companionship of our family and friends. It's the best time of the year, a time I cherish. But I'll be celebrating the holidays differently this year, and I hope you also celebrate it responsibly and safely. There has been excellent progress on the development of several effective vaccines and therapeutics, supported in part by innovative work at UTMB and researchers around the globe. Plans are underway to make these vaccines and treatments available in the coming months, and we look forward to the day that we are able to resume these sessions in person at Space Center Houston. For now, we at UTMB wish you the best and the healthiest of holidays and invite you to sit back and enjoy some of the great speakers and this Thought Leader Series sessions. Thank you.
Hello, I'm William T. Harris, President and CEO of Space Center Houston. We're a dynamic science and space exploration learning destination. We're also a nonprofit science center and serve as the official visitor center for NASA Johnson Space Center. We share the story of human space exploration, past, present, and future, with more than 1.25 million visitors annually from around the world through on-site and virtual experiences. Thank you for joining Space Center Houston's Thought Leader Series program, Illuminating Space, presented by University of Texas Medical Branch. Our series features space and science experts from across the country who provide insights and perspectives on space exploration. The International Space Station orbits Earth every 90 minutes, so the astronauts experience 16 sunrises and sunsets during a 24-hour period. These rapid changes between light and dark affect crew members' circadian rhythm and can cause sleep disruptions. NASA has been studying light and its effects on space exploration for decades. Today's program will delve into scientific research and how light illuminates space. You will hear from leading experts on this interesting topic about the power of light. Through our Thought Leaders series and other programs, Space Center Houston makes science and space learning accessible to everyone. Space Center Houston is open with new exhibits, new live shows, and spacious outdoor experiences with health and safety measures at the forefront of our daily operations. We invite you to join the Space Center Houston this holiday season during Galaxy Lights, presented by Reliant. Galaxy Lights is open nightly through January 3rd. It's an immersive holiday light tradition, bringing guests the most interactive and technologically advanced light display in Texas. Explore the center in a new way with stunning space-themed light installations, 2 kinetic light shows with suspended moving lights, and photo stations set among actual space artifacts. This year, we celebrate the 20th anniversary of continuous human habitation aboard the International Space Station, with all new lights around the world display surrounding our permanent exhibit outdoors, a flown SpaceX Falcon 9 rocket. For a list of activities and to purchase advance time tickets, visit spacecenter.org. As we navigate this unique period, Space Center Houston is committed to supporting our community with authentic science learning experiences in a safe environment. You can save time in line with advanced time admission tickets. You'll experience one of our most popular experiences, the NASA Tram Tour, which takes guests behind the scenes at NASA Johnson Space Center. Through the Space Center Houston free app, you can select and reserve seats on the tram tour you wish to board at a designated time, so no more waiting in long lines. Plan your journey with us today, again at spacecenter.org, and review our Know Before You Go guide for more information on planning your visit. And now on with our December Thought Leaders panel, Illuminating Space, presented by UTMB. Our panel of experts include Dr. Stephen Lockley, Dr. Robert Hurt, and Hanya Muradami, who will discuss what light is and how we see it, and how it affects space exploration. You will learn how scientists are studying the physical and psychological effects of lighting aboard spacecraft, as well as lighting conditions in future space habitats, and how this is relevant to our everyday lives. Let me introduce our panelists. Dr. Robert Hurt is an astronomer at Caltech IPAC with a research background in star formation and galaxies. He specializes in data visualization, the development of illustrations and video to help explain science to the public. His data visualizations span a wide range of NASA missions, including Spitzer, Kepler, WISE-NEOWISE, NuSTAR, and GALEX. He's developed immersive virtual reality and planetary experiences and is part of NASA's Universe of Learning team, contributing to a number of projects, including AstroPix and Universe Unplugged videos. Dr. Stephen Lockley is a neuroscientist in the Division of Sleep and Circadian Disorders at Brigham and Women's Hospital in Boston, and an associate professor of medicine in the Division of Sleep Medicine at Harvard Medical School. Dr. Lockley has studied circadian rhythms in sleep for over 25 years, specifically the impact of circadian disruption, long work hours, sleeplessness, and sleep disorders on performance and health in many groups, including astronauts. He's researched the properties of light for resetting circadian rhythms and alertness, and ground-tested new LED lighting now installed in the International Space Station. He co-leads a current study to measure the impact of tunable LED lighting systems in astronaut circadian rhythms, sleep, and performance aboard the ISS. He studied circadian rhythms and sleep in Antarctic stations, is developing new biomarkers for circadian rhythms and sleeplessness, and has studied the impact of lighting interventions for NASA, Hera Analog, the Mars Phoenix Lander mission, the Mars 105 Day Study, and Mission Control. Ms. Hanya Maratami is a lighting designer and researcher with a background in visual communication and human-centered design. She's an expert in lighting design for extreme environments, specifically outer space. She's interested in the visual and non-visual effects of light on human chronobiology and cognitive performance in extreme, isolated, and confined environments. As part of her master's studies, she has extensively researched the role of light on human psychological health and the effects of deprivation from earthly light phenomena through long-duration space expeditions and human colonization of planets beyond Earth. Her passion is promoting human well-being for extreme living conditions, has led to winning first place in the finale of NASA's Phase 3 3D Printed Habitat Challenge in 2019, along with her team AI Space Factory, and first place with her team Mars Colony 10 in the 2018 Mars City Design Competition. Our panelists will now provide a little more information about their backgrounds and the scope of their work, followed by a moderated discussion, which I'm really looking forward to. First, we'll hear from Robert Hurt. Robert.
William, thank you for that fantastic introduction. So I'm going to come at this maybe a little backwards from where everyone else is coming from. The topic today is illuminating space, but I sort of want to flip it around because as an astronomer, I think of space as the one thing that is not in need of illumination, because space illuminates us. Everything about our lives here on Earth is affected by the way the universe provides light. Now, obviously, the sun is maybe the most obvious element of that, the sun, the light from the moon. But the universe itself is luminous throughout space, near and far. And no matter where we point a telescope, we can see evidence of that. Just to step through a few examples. When we look out and we find the iconic images of nebula through space, right? These are regions in which new generations of stars are forming from the gas and dust that fill the voids between the stars. Images in the infrared, the visible light, all show us these different views of incredible textures and clouds and structures. They are all the stories of how new stars are built that provide the light that here on Earth we so rely on. The next slide shows another example of an expanded region, here a mix of dust and gas and stars all embedded throughout. Of course, stars themselves create nebula that we see in these images. When stars die, stars like our sun die, they actually will puff out and their outer envelopes will leave behind a residue, an expanding nebula of material that gets recycled back into space, whether it looks like a series of concentric shells or jets that are blowing material out back into space. This is part of the cosmic recycling process, where some of the heavy elements forged in stars get recirculated back out into interstellar space to become the components. When heavier stars than our sun die, they die in these dramatic explosions that forge even heavier elements up through iron and uranium, and those get returned into space through these fantastical shells of supernova remnants. But then looking out beyond our galaxy, our own home of a few 100 billion stars, we see that we are but one of trillions of other galaxies in the universe, all lit up here with the ensemble of the combined blended light of all the stars and all of those nebula blending together. Some, of course, are spirals. Others are galaxies we call ellipticals, more like sort of symmetrical beehives of stars, sometimes with rings of dust that are seen in this image of the Sombrero Galaxy. And in this view of the Pinwheel Galaxy, we actually are combining light from across the spectrum to show all the different facets of what's going on between the light of hot stars, the X-ray glow of regions around neutron stars and black holes, to the glowing dust seen in the red tunes here. These images actually encompass the entire spectrum of light and show us the universe is just brilliant and glowing. But this leads us to a very fundamental question I want to step back and ask. And that question is simply, what is light? Now, when we think of light, it's very possible that one of the first images that come to mind is that of a rainbow or a prism, right? The idea that light is this blend of materials, blend of colors that our eyes can see. In the case of a prism, we learn early in school that you shine a beam of white light through a prism and it refracts. It splits up into a spectrum of color that represents, all of the incredible things that our eye can pick up out of light. But it's a very human thing to think that this is it. This is all that light is, the things that our eyes can see. But our eyes are just one product of biology on one world subject to a particular kind of light from one class of star. And it turns out that the investigation of what light really is had to expand vastly beyond pure human experience. Sir William Herschel, hundreds of years ago, fired the first volley, I think, in that blast of understanding when he discovered, using tools no more complicated than a thermometer and a prism with light passing through it, that there was light that could be detected beyond the edge of what we see as red, something that we now know as infrared. And that is still light, even though it's not light that humans can see. We'll run that forward a few hundred more years through people like Maxwell, through Einstein, and what we arrive at is this idea that light is a wave of electric and magnetic fields. And as such, waves have extent, they have a wavelength, they have a spacing between these fields. That wavelength defines what we consider to be the color of the light. Of course, the full spectrum of light goes far beyond that tiny slice that we call visible light, the visible merely because that's how it looks to our human eyes, right? At the shortest wavelength end and the highest energies, we have gamma rays, X-rays, ultraviolet. And as you go to longer and longer wavelengths of light past the red, we reach the infrared, into microwaves and radio. It's all, we give it different names, but it's really all a continuous, uniform selection of all the same kind of phenomenon that manifests in different ways. But for this incredible spectrum of light, even though there are things that our eyes can't see, we can build tools that help reveal that. All of the images that I've shown before are actually compiled from the data taken by a variety of missions that NASA has built or worked with that expand our vision from the X-rays through the infrared, the radio, and beyond. So by picking and choosing different parts of the spectrum, we can reveal all the incredible colors that the universe is showing us, whether or not they're colors that our eyes are designed to see. I like to think of this as translation, right? We want to take light from parts of the spectrum that aren't in our vocabulary, our visual vocabulary, and we can translate that back into the color images like I was showing that we can perceive. So where does this light come from? Well, the remarkable thing from the viewpoint of physics, I think, is that almost everything that you see in this light can be attributed to one of two kind of phenomena. One is something that physicists call blackbody radiation. This is the intrinsic radiation, the glow that every bit of matter in the universe has, just defined by the temperature that is at. when you have matter that's heated up to relatively warm conditions like electric elements on a stove, that starts to glow in the red part of the visible light spectrum. If you heat it up even more to the temperature of a filament in a tungsten light bulb, that color tends to shift more into the yellows and to the oranges. And if you get a really, really hot light bulb, it even starts shifting into the whites and to the blue whites. Our sun itself, at a temperature of about 6,500 degrees Kelvin, is sort of finds white, but a star that's even hotter than the sun takes on a blue color. So much of the universe is just determined by the glow of material. Now, if you're a little cooler, like humans are, you actually glow in the infrared, but our eyes don't see that, and we don't think ourselves as luminous beings like we are. So in astronomy, if you look out at these images, everything that you see in this picture, most of this is coming from either very hot things or very cool things, dust clouds that can be cooler, stars that are a lot warmer. But there's another element of where light comes from, and this is what again a physicist would call spectral line emission. Now, in our day-to-day experience, this can be thought of as what we see when we look at neon light bulbs or even LEDs. So spectral line emission is, in our sort of day-to-day experience, the kind of light that you see when you maybe see neon signs or LEDs. This is the light that's emitted due to the nature of how atoms and molecules are built, with electrons spinning around charged nuclei and constrained by the laws of quantum mechanics, so that they are only able to move at very discrete steps of energy. And when an electron goes from a high energy state to a lower one, it emits a very specific wavelength of light, a very precise color. So this is the other thing that we see when we look around the universe. All of these images of beautiful nebula that you see that are taken in visible light, almost all the glow that you see here that isn't starlight is coming from the glow of atoms and molecules, of gas and of dust that have been excited and are emitting these very precise wavelengths of light at very specific frequencies. And that gives us these vivid colors. To an astronomer, these colors actually tell us the physics of what's going on. They help us fingerprint specific chemicals to identify atoms and molecules in distant clouds, hundreds, thousands of light years away. It helps us figure out things like temperatures and densities of material. It's really an incredible measuring tool for studying the details of something that's so far away that we will never reach it in a human lifetime or even centuries of travel. So looking out at the universe, I see that as a vastly illuminated place. The light spans the entire spectrum of light, and some of it is in that range that our human's eye perceive as color. So I, on this note, will turn it over to our next speakers to start talking about how light is perceived by humans and how we can play and manipulate that to create the psychology and effects that we want.
Thank you, Robert. That was absolutely fascinating. These images are breathtakingly beautiful. So I look forward to asking you more about those when we get to our discussion point. Now I'm excited to turn it over to Dr. Stephen Lockley. Stephen.
Thank you, William. So why are we interested in what light does to us here on Earth? We've evolved in a very strong light-dark cycle. The Earth spins once a day, and anywhere on the Earth you would experience usually a day-night cycle where some part of the 24 hours is light and some part is dark. And that's been a very strong environmental time cue that has caused us to organize our biology around a 24-hour day. And so we have a clock in the brain that keeps time on its own, that is a 24-hour clock that is synchronized every day with that 24-hour light-dark cycle. And some of the things that are driven by this clock, this circadian clock, are things like sleep, your alertness, your performance, your metabolism, and many, many aspects of our day-to-day biology. Now in space, we have a real challenge because we've moved away from Earth and we don't get the same type of light-dark cycle in space as we would on Earth. And so as William said in his introduction, astronauts on the space station orbit the Earth every 90 minutes and they see 16 sunrises and 16 sunsets every day. And so here's an example of 3 sleep-wake cycles of astronauts across a long mission. And as you can see, that's clearly not a regular schedule. You can see that the sleep-wake cycle shifts a little later, then shifts earlier. And some of this is due to the work that the astronauts have to do on the space station, but some of it's also due to the inability to stick to a 24-hour Earth day. And in fact, astronauts don't sleep very well in space, partly because of this. They only sleep about 6 hours a night on average. But when they're sleeping at the wrong circadian time, when they're sleeping at the wrong time according to their body clock, they sleep even less, just over 5 hours a night. And this is a problem because space is a very dangerous place, and we need people to be alert and able to perform well to make sure that they're safe and their crew members are safe. So what do you notice about this photograph? What has gone wrong here? Well, you can see that the astronaut's boots are on the wrong feet. And so this looks like a fairly minor problem, and it probably was. Nothing bad happened as a result of this, but it shows an example of the type of slip or lapse of attention that could put the safety of crew members in jeopardy, because this might now make it more difficult for the crew member to walk around and attach onto the space station because of special fittings on their boots. And so astronauts really do need to be at the top of their game, and sleep and circadian rhythms are an important factor in determining how sleepy they are. And so what does light do? Why can light help us? And so much like the ear has two roles, the ear helps you hear and helps you balance. The eye also has two jobs. First of all, the eye helps us to see. It helps us to see that visible light that Robert talked about, so we can see things in our environment. But there's also a different photoreceptor system in the eye, which is not helping us see, but is helping tell the brain whether it's daytime or nighttime. And this is a photoreceptor system in a different part of the eye, which I'll show in a moment, and is most sensitive to blue light. It's most sensitive to blue light in the 480 nanometer wavelength range. And you need this light for two reasons. The first main reason is to synchronize the clock, and so we need that daily light-dark cycle to synchronize our rhythms. And if we don't get the right light-dark cycle, things go wrong. And many of you have experienced this. If you've had jet lag or worked night shifts or slept in as a teenager, all of these are examples of circadian rhythm problems because people didn't have exposure to the right light-dark cycle. Light is also, though, a stimulant. As well as keeping our clocks in sync, it also directly alerts the brain. And so we can use light as a stimulant, and we know we need it because we use crazy amounts of caffeine in society, and so we're very sleepy as a population. And so anywhere where you want people to be alert and awake and productive and safe is a place where we can use light effectively. And we need to incorporate that into design. We want your environments to be well lit. And so the challenge to designers is to combine both the biological effects of light to allow us to see, and also these non-visual effects of light to allow us to reset our clocks and be alert. So how do we do this? Here's a picture through the eye. Light comes in from the top of this diagram and then hits the rods and cones at the back of the retina. They're shown there in the blue colors. But lots of experiments were done both in animals and in humans where the rod and cone layer was either damaged or was taken out experimentally. And you would think that all the effects of light would stop, because we thought until that time that rods and cones were the only photoreceptors, the only light detecting cells in the eye that could detect light. But in fact, even after the rods and cones were removed, we still observed circadian responses to light. And in 2000, a novel light detector was found in the eye, in the ganglion cell layer of the eye, which is only in a very small proportion of those ganglion cells, but they contain a light-sensitive chemical, a photopigment called melanopsin, which detects blue light. And in the bottom right, you can see where those cells project to. They project right to that biological clock in the middle of the brain. So you can see there the pathway right to the circadian clock. And in the bottom left, you can see that these cells are spread all across the retina. And so they're not really there to help us see, where we would have a much bigger density of cells. They're there to really tell the brain, are the lights on or off? Is it day or night? And so we have two light systems, if you like, into the brain. We have this system that allows us to see, and that's the traditional visual system through the rods and cones, shown here with the green pathway. And then we have this blue sensitive novel system which detects light to tell the brain essentially the time of day. So how can we take advantage of this information? Well, now we can start to manipulate light to either stimulate or not stimulate the circadian clock or the alertness signals in the brain, separate and apart from vision. And so we can now develop lights that can change both the intensity of the light and the spectrum of the light to make sure we're seeing the right light at the right time to help our biology. And this is quite straightforward. If you're in a place where you don't want to sleep, if you're at work or at school, or you're at home in the daytime, you want to see blue enriched white light, high intensity blue enriched light that tells the brain this is daytime, I want to be awake, I want to be productive. And you need that all day to tell the brain to be awake and productive all day. But then in the evening before sleep, you want to start to calm the brain down and start to feel sleepy. And so you need to dim the light and have less of those blue wavelengths. And so if you redden the light, make it more of the orange-red spectra, you start to calm the brain down, prepare the brain for sleep, and allow the brain to get better quality sleep. And so NASA has really embraced this technology. NASA has been funding basic research on this since the 1990s and has led all the way now to new lights on the space station. And these lights have 3 settings, although they can produce many millions of different settings if we wanted to. They have 3 settings, which is a good daytime light, which allows people to see very well. But then if they need an alertness boost or they need to shift their clocks to do night work on the space station, they can turn up both the intensity and the blue content. So we have a high circadian, high alertness setting. And then in the evening before sleep, we have a pre-sleep setting, a low blue or red enriched light, which then helps the astronauts calm down, calm their brain down, and get ready for sleep. And so here you can see Dr. Kate Rubins installing one of these new lights on the space station. About 80% of them have been installed. It's ongoing, and we're doing studies to look at the impact of this lighting. And we've also put the similar lights in the HERA analog down at Johnson Space Center, which is a human exploration research facility where people live for 30 or 45 days or longer to mimic spaceflight. And so we've been examining the impact of this type of tunable lighting in that analog there at Johnson Space Center. But it isn't just specialized places where we can use this light. The very same principles can be applied in the classroom. Here you can see 2 classrooms lit with a blue enriched alerting light on the left-hand side, which we want to have to help pupils learn, as opposed to the traditional lighting, which is that yellowy sort of fluorescent 4,000 Kelvin light, which isn't really helping anyone be alert. Similarly, in care homes, people are starting to study the impact of having bright blue enriched light in the daytime in care homes and hospitals, and then having that blue depleted dimmer light in the evenings to help people sleep. Now, as we try to go to Mars, Mars is a different challenge even to the space station. And so the Martian day is about 40 minutes longer than the Earth day. And so a Martian sol is hard to synchronize to. We have to push our clocks later to live on a Martian day. And here are 3 laboratory experiments, simulations in a laboratory here in Boston, where we tried different light settings to try and get people onto a Martian day. And it's only the 3rd one where we had 100 lux, so reasonably moderate light during the daytime, but only with a big pulse, a very bright light at the end, could the researchers achieve synchronization to a Martian day. And so you have to have very specialized schedules if you want to synchronize to Mars. The other way we've done that is using blue light, but at the right time. And so these are data from the Mars Phoenix lander mission, where people lived on Earth, but on a Martian day, so they could communicate with the lander at the right time. And you can see on the left that drift in pattern, that drift in the sleep, wake and work pattern, getting later and later as they lived on this longer day length. And you can see there on the right, the blue light boxes we installed and the blue light exposure, which helps shift them to that Martian day. And so we can get people on Mars, but it's quite hard to do. We need to time the light properly, and we need to have the right type of light at the right time to do that. And so we've gone from a situation in the top left, where we had people velcroed to the wall, essentially, in order to sleep, to the development of new crew quarters in the middle, where crew members now have their own individual rooms, essentially, to allow them to sleep a little bit better. And more recently, those crew quarters have been fitted with the tunable lighting so that astronauts can get the right light at the right time of day. And here's flight engineer Ricky Arnold explaining how it works.
Well, here in space, we kind of have to do it artificially. So we have these nice crew quarters. It's about the size of a refrigerator. It's very quiet. The space station can be a little noisy, but it's very quiet in here. And we can control light with a light switch. If we are just middle of the day, we have a light like you're seeing right now, which is just this kind of standard lighting. It's getting close to the end of the evening. You want to dim the light a little bit, kind of for the end of the evening. Or if you're going to be up late and you need to keep awake, we have a really bright light setting. The other thing we have is off. Good night from the ISS.
So light is really important to help our health and well-being, and we have to make sure we get the right light and the right dark at the right time. Thank you very much.
Thank you, Steve. That was absolutely fascinating. I have so many questions I want to ask you about this, and I'm sure that many of our visitors will be interested in this conversation as well. But before we have the discussion, I'd like to bring up our third and final speaker, Hanye.
Thank you, William. It's a great pleasure to be a part of this conversation. My story starts from when I was being trained as a lighting designer, learning about all the visual aspects of light that, regardless of the source, natural light, of course, from our sun, or electrical lighting, it quite literally renders the world that we exist in, depending on its directionality, intensity, color, and so much more. It affects our perception of a space, our mood, and potentially even our emotions. It interacts with our surrounding objects and environment, creating these natural light phenomena that we're used to seeing all around us. And I'd argue that our lives and our world would be really dull and monotonous without them. So the visual aspect of light is already quite complex and a really powerful tool in design. Then learning that light has a whole non-visual aspect to it that affects our body, our mental and emotional well-being that Steve just explained beautifully. I thought, how incredible would it be for a designer to utilize this knowledge to achieve a more holistic design? That led me to exploring extreme situations where I started looking at conditions and environments that humans have lived and studied, where light has, for the lack of a better term, an unconventional presence, rhythm, or is absent altogether. Understand their effects on the inhabitants. So, for example, the day-night cycles in Antarctica, where there's an extended period of light for half the year and an extended period of darkness for the other half, in addition to the fact that it's really cold and the color palette gets really old very fast, and how that affects the residents' circadian rhythm and their mental well-being. Speleologists living in caves, avoiding any external cues for time of day to let their circadian rhythms actually go on a free run, eating whenever they feel hungry, sleeping whenever they feel tired, and how this affected their perception of time. So the relationship between availability of light and time in this case was really interesting. In the submarines, looking at the absence of natural light, in addition to isolation and confinement, while having strict work schedules, and how it has led to frustration and behavioral issues. Solitary confinement, where in addition to some of the things that we have already mentioned, it also removes autonomy and humans having any control over the space and over their environment, including lighting, as a form of punishment. And of course, when I started looking at any living environments beyond our atmosphere, I was humbled by how much I didn't know and wanted to understand where in the list of priorities does light really sit, knowing that almost everything is different out there from what we were designed to endure and survive. Which brings up the idea of habitability. So bear with me, we're taking a step back, looking at a big picture view of the issue, and then we're going to get back into lighting again. On the bottom of the diagram, we have what humans need to thrive in an environment, and a duration of a mission or the stay increases the importance looking from left to right, meaning In a shorter mission, you can probably get by providing the physical needs and the safety of those that are doing the mission. And as it gets longer, other aspects that are more emotional and psychological gain importance as well. However, these needs do overlap, meaning that you don't need to finish one in order to move to the next, to satisfy the next. Also, light falls into the basic needs, as you can see on the top part of the diagram. But the greatest lesson I learned, which is the whole point of this slide, was where stakes are high, you need to become more than a lighting designer to understand priorities amongst all other disciplines, to identify restrictions and opportunities, and to provide a holistic design that could solve more issues than solely the illumination of a space, which is why I'm a huge advocate for cross collaboration between engineers, scientists, designers, and other specialists in order to achieve the best possible outcome. Because on Earth, we're lucky that some of these stressors are generally, having an atmosphere will take care of radiation. And hopefully, if you have a home to go to, some more of the stressors will be resolved. And we'll mostly need to focus on esteem and self-actualization, maybe. Now let's have a quick look at an approach to designing lighting for a habitat on a different planet. I needed to understand the characteristics of another planet, so it was easier for me to lay out a comparison between Earth and Mars in terms of anything that would affect the lighting and other fundamentals, of course, and find the restrictions and opportunities there. For example, we know that Mars is further away from the sun in comparison to Earth, so it receives less natural light. Its thin atmosphere, lower gravity, and orbital path around the sun causes dust storms that sometimes last for months, all making daylight harvest harder and less dependable as a source for us to use to illuminate the interior of a space. Not to cross it off completely, but just saying it's really difficult. The dust also makes the sky more butterscotch and doesn't let the shorter wavelength, or what we call blue light, through. Days are also, as Steve mentioned, 24 hours and 40 minutes, and the year is almost twice longer than what we experience on Earth. The lack of an effective magnetic field allows exposure to radiation, which all in all means that the crew needs to spend most of their time inside of a habitat. Okay, I'm not going to talk about the architecture of the habitat and would like to ask our viewers to do some research on the material my friends at AA Space Factory have provided online, but just wanted to point out that the habitat has a dual shell design that keeps the living environment separate from the outer shell. And this characteristic came in handy when we were designing the lighting of the habitat. Okay, we're looking at the main lighting system installed on the outer shell. Let's look at it a couple of times and then we'll go to the next slide and unpack it. Now, here's what we saw. First of all, the habitat has a multi-purpose skylight that, in terms of lighting, it can harvest whatever available light while also providing a view to the outside world. In the morning, though, we're going from left to right. The system automatically turns on, providing the crew with a dose of blue-rich light to support their biological rhythms and help them feel focused and productive during the day. Its directionality, which light is coming from above the head, is also inspired by the position of the sky. Towards late afternoon, we have a transition period that helps the crew to get a sense of time of day. And this is actually a really good example of the importance of cross-collaboration, because I learned recently from Dr. Lockley that we might want to push this transition toward later in the day to avoid any possible negative effects on the circadian rhythms. In the evening, the blue-rich has gradually given its place to a warmer uplight, cueing the crew to prepare for nighttime activities. And in this case, its directionality is inspired by the calming effect of flames of fire. So it comes from below, basically. And then eventually there's a full automatic shutdown for the sleep of the crew. Now, in my opinion, and from the feedback we've gotten from the subjects of projects like High Seas, to avoid monotony and as a form of visual relief. There's another important scene that supports the emotional well-being of the crew, where the lighting system has the ability to connect to the audio system, for example, and recreate natural earthly light phenomena, maybe like a thunderstorm, or to celebrate holidays and birthdays, but basically to change the mood inside. Yeah, thank you.
That is absolutely fascinating, and I love these habitat models. So now we're going to have a conversation with our panelists, and I've got a number of questions here, but I wanted to go back to Robert for a second, and we hear about light years. What is a light year?
So sure. So a light year is actually sort of the go-to way that astronomers measure distance in the universe, because it's actually based on light itself. It's the distance that light travels in the course of a year. And so just to give a sense of proportionality, light that we see from the sun actually left the sun 8 minutes before we saw it. Okay, it takes 8 minutes for light to travel to us from the sun. Round trip light times get progressively longer and longer as you move out towards the outer planets in the solar system. It starts to be measured more in hours. And then the nearest star to our own is about 4 light years away. So that sort of begins this scale of the universe. The size of our own galaxy, the few 100 billion stars that we're around, that's about 100,000 light years across. So it takes light 100,000 years to travel from one side of our galaxy to the other. And to the very nearest galaxy, it's about 2 million light years away. And then as far out as we can see in the universe takes out on the order of 13 billion light years out from where we are. So it's sort of the way of sort of establishing equivalency between sort of distance and time, and using light as that translation marker.
Well, that is so interesting, because we always hear about the reference to a light year, and then actually seeing these incredible images from deep space, and you were saying that some of them are hundreds of thousands of years away, right? Incredibly deep out into space. It's really quite remarkable that we even can capture that illumination.
Yeah, no, I mean, most of the images you see in astronomy, if they're nearby nebula, are, they are hundreds to thousands of years old. Galaxies are millions to billions of years older. And so light also acts like a kind of a time machine for us as well as astronomers, because the further out we look in the universe, the further back in time we look. So we get a chance to see what the universe was like in different stages of its own evolution since the Big Bang.
Well, I know there's been a lot of conversation about what is black hole and different matter, and I know there's a really interesting experiment ongoing now on space station with the alpha magnetic spectrometer, right, which is looking at kind of the fundamental of physics of what is space and where does it come from. Are you doing any using any of that data at all in the research that you're doing, or looking at illumination in space?
Not myself. No, my focus is more the data that comes from the astrophysics missions that NASA flies. So the telescopes that are unmanned, floating off, either orbiting the Earth or drifting off in their own orbits behind the Earth.
Well, very good. So soon you'll have James Webb, as soon as we get that into space, right?
Exactly.
That's fantastic. Well, Steve, I wanted to ask you, I was very intrigued by your presentation, and I'm also thinking about kind of the practical implications for us here on Earth. And it's very interesting to hear your comments about and how astronauts are testing the different kinds of light, from the blue light to the red light. Is that something that we can obtain commercially if someone wants to try this at home? Are those the color lights available for the regular consumer?
Yes, they are. They're not quite as sophisticated or expensive as the lights that are on the space station, but the principles are the same. And so NASA has really informed the development of these Earth benefits, because NASA has been funding research in this area for a long time. And so you could now go to Home Depot or to another place and get lights which have a different spectrum or look a different color. And so in the daytime, you want lights that are very blue looking or cool looking when people talk about color temperature. And those have a high Kelvin value. And so Robert was talking about the Kelvin value of light. And so something 5,000 Kelvin or 6,500 Kelvin would be a blue enriched white light that has those alerting blue wavelengths in them. But then in the evening, for as long as possible before sleep, you want to dim and redden that light and have a lower color temperature, something say around 2700 Kelvin, which again you could buy very easily. Now, Kelvin's not quite the right way to measure the light. There are in fact new ways that we quantify light, but for most people it would be okay to buy a high color temperature light for daytime and a low color temperature for the evening. And you don't need a fancy light, although some companies sell lights that do change automatically, and you could use those. But you will probably have two circuits in each of your rooms, and so you probably have a light in the ceiling and then a table lamp or a bedside lamp. And so you could put the high color temperature, high intensity blue and rich light in the ceiling for the daytime, and then in the evening, for as long as possible before bed, turn that ceiling light off and then use your table lamp or bedside lamp or another light source. And so you can either buy a system which does it itself, they're out there, or you can just put the right light bulb in and use the right light at the right time. And you'll get exactly the same benefits as the astronauts. They just have a fancier system to do it.
Well, Steve, I also wanted to ask you about how we have become obsessed with our devices, and especially now during the COVID-19 period when we're all kind of in semi-self-isolation at home and we all live on devices using different technology to communicate, and we are using these all day. Is the illumination from a screen from your iPhone or a Samsung phone or your laptop or tablet, does that affect your sleep cycle?
Yes, the light coming from electronics is certainly having a biological impact on you. So many electronic devices pump out exactly the blue wavelengths that alert the brain. And so in the daytime, that's okay, because those wavelengths are helping keep you alert and helping keep you productive. But if we start to use them in the evening, and I'm talking about using them within about 3 hours of bedtime, they're going to have a negative effect on your sleep, on your circadian rhythms, on your alertness. And if you do that over many, many weeks and months and years, you may develop longer term problems for things like insomnia. And so we first of all should not use those electronic devices very close to bedtime. And so stop using them as long as you can before bed. But then if you can't stop or you have to work, then there is software available that will help to dim and redden the screen. So many devices come with that pre-fitted now, where you can change the screen output to that reddy orange and dimmer color in the evening, or you can find software for free online. There's one group we work with called f.lux that has free software that you can download on your devices, and that will automatically start to change your screen and make it dimmer and redder in the evening. Also try and keep devices away from the eyes. The closer the light, the closer devices to the eyes, the worse it is. And so, don't be using phones and things which are very close to your eyes in bed, in the bedroom. Keep that out of the bedroom and keep the bedroom nice and dim and dark for sleep.
I have to say, I know there's a feature on my new iPhone where you can have a day-night and a nighttime setting, and automatically after sunset starts dimming the screen, I've noticed, which is pretty interesting. So it sounds like it may be aligned with that scientific information.
It's helping, but it's not the same as darkness. And so yes, that's going to help, but the best thing is to not use your devices very close to bed, because it will affect your deep sleep. It will affect your sleep timing, and in the long term, we think can cause health issues.
So Hanya, I'm curious, in your work, are you taking this into account with your clients, or when you're working on light design for a space? Is this something that's now an important consideration when you are creating a space, say for a corporate setting or a home or some other space that humans will be occupying?
Yes, absolutely. The good thing about this is that the science is science. It doesn't change. And for some clients that are interested into elevating the experience and spending the extra money, it's absolutely applicable. We do look at systems to create variation in the space to either turn the space into a multi-purpose area or just for emotional support and psychological support. So yeah, the knowledge is absolutely transferable.
Oh, that's fascinating. So I understand that we do use animal models many times. And so I'm curious, Steve, do you find that as an accurate for humans and using animal models? Because of course they've evolved to live in a world that rotates in 24 hours a day.
A lot of the very early discoveries about how light affected our biological clocks was done with animal studies, although it gets a little bit complicated because many of the studies are done with rodents, and rodents are nocturnal. They're active at night and asleep in the day, obviously opposite to humans. And in fact, if you shine a light on a mouse, you'll make it go to sleep. Whereas if you shine a light on a human, it will wake us up. And so a lot of that research was done to understand the neuroanatomy, but it turns out that that melanopsin system, that blue light sensitive system, is there in mammals, in other mammals. It's there in mice, it's there in rats, and people are still studying those systems to really understand how that works at a molecular level, at a cellular level. But it's the same underlying principle, and that makes sense because for really nearly all organisms on Earth, that light-dark cycle is key. And so it really determines when you need to be active, how you can find food, how you can find a mate, how you can survive. And so making sure that you have a clock which interacts properly with that external world, that external light-dark cycle, is key to survival. And when people have done experiments that mess with clocks or mess with light, it doesn't turn out well for the animals. But the same is virtually true for us. If you are a shift worker who's worked night shifts for many, many years, you do have a higher risk of chronic diseases like heart disease, like depression, certain cancers, diabetes, and so on, because it's very unnatural for us to be awake and seeing light at night. And so when we, over a very long time, keep readjusting that system and stay awake at night and sleep in the day, that has these long-term health consequences. Anytime that the brain sees light, it thinks it's daytime. And so if you see light after dusk, if you see light at night, the brain thinks it's awake or asleep at the wrong time and tries to do something to change it by shifting its clock, alerting the brain, and so on. And so really keeping that stable light-dark cycle, bright days, dark nights, is really key to health. And if you have to do shift work, then we need to try and adjust you as quickly as possible or minimize the amount of time that you're doing shift work.
Well, I have to tell you, I can relate to that. When I was finishing my degree in research psychology, I had an internship one summer at a psychiatric hospital, and I was the fill-in for people going on vacation. So I did a month of days, a month of second shift, and a month of night shift. And I almost killed myself leaving after the night shift many days because I had such a hard time adjusting to the cycle, and I've had personal experience with that. I realize how tough it is.
It is, it's very difficult. And there are other examples, jet lag and delayed sleep phase disorder. And as Hanya was saying, there are many environments which make it even harder. So people in submarines have problems synchronizing, just like in Antarctica as well, and then also during space flight. And so we have to take the provision of light very seriously. It's not just about sticking a light bulb on and thinking we've solved the problem. We really need to be proactive in developing lighting for all the new space habitats that we're going to need in the future. It's really something we need to take very seriously.
Well, I have a question actually for all three of you, which is, as I'm looking at Robert's background, and it's just absolutely fascinating, seeing these representations of the various celestial bodies. And we as humans are incredibly attracted to light. We have a light display currently at Space Center Houston, and people love it. They're just fascinated by light and the colors of light. Why do we as humans have this fascination? Why do you think that we're so drawn to light? Beyond the fact that it enables us to live our lives, and we're evolved to live life around light, but we also have this very emotional connection to light.
As we all talked about, I personally think that because we have such a basic, complex relationship with light in general, which includes the visual and non-visual aspects of it, it just makes us so much more sensitive to it. And the way it creates memories, the way we perceive an environment, the way it reflects off of different materials, objects, is all things that make us feel nostalgic, that remind us of things, of memories. I think it's basically because of our complex relationship with light that we're so drawn to it.
I might take a stab at that from the viewpoint of astronomy and the fact that as probably amongst all of the sciences, astronomy is, I think, just one of the most widely appealing to people, because the imagery that we get, the idea that we are pulling these images of light from the universe, throughout the spectrum, provides pictures that show people these patterns and these color combinations that exist outside of their day-to-day experience. I think that a lot of what drives the appeal of the imagery is things that really just blow your mind with something that's nothing like you see in the world around you. And I suspect, this is where I'll put on my I haven't been trained in psychology hat, but I suspect some of this is tied to our sort of biological motivations to notice when things don't fit naturally in the world around us, right? We're hardwired to notice weird outlying things occurring in the world. And so the existence of a strange color or a strange pattern, right? This is part of our cueing to like, oh, what's going on over there? Do I need to be concerned? And I think on some level, the abstractness and the interesting color palettes of astronomy images might actually kind of tie into some of that psychology of how we react to things that aren't like what we're used to seeing in the world around us. I might throw in that, I've been just fascinated by light myself and color. I've been accused of having a color fetish. It's my whole home actually is installed with a variety of off-the-shelf lights that I can use my phone to change the color, or I can just call out what color I want the room to be, and I actually even have it set up so that lights come on at different times of day as cueings, and by the time it's time to go to bed, all the lights start drifting over into oranges. And so I've certainly taken the cue to build my own living space around a lot of these principles as well.
So, William, I would say when we think about what light is doing for us, we're really mostly thinking about the light we can see, the visual effects of light. But of course, now we need to keep in mind that there is this separate second system which is detecting light to really control the biological effects of light. And that still works even in totally blind people who have no vision. And so if we talk about the importance of light, we've got to think, well, what happens when you lose the ability to see light? And as I mentioned in my talk, there were studies of both blind animals and blind humans who had no rod or cone function, but their eyes could still detect light to synchronize the body clock. And that was discovered back in 1995, and we've since found 9 people in the world who have no vision, have no ability to see light at all, yet their eyes are still capable of detecting light to tell the brain whether it's night or day through that blue light melanopsin system. And so you can completely separate the visual effects of light, what we see, and the non-visual effects of light, which are governed by that melanopsin system. And so we all take light for granted. We don't go out every day and say, I'm going to set my clock now, I'm going to see light at 7 a.m. If you live in a light-dark cycle, sometimes even if you can't see it, then the clock can synchronize to that light. Now, unfortunately, most totally blind people can't in fact do that, and they're unable to synchronize and have a disorder called non-24-hour sleep-wake disorder, because their internal clocks can't synchronize every day. And so light is absolutely necessary for us to be synchronized to the Earth day. But we can get the benefits of light without seeing it. And if you can't see light, doesn't mean that those emotional issues necessarily occur. And so we need to think about light a little differently now from what we see versus what light is doing to us biologically.
That's fascinating. So I wanted to go back to that for people who are blind and are not, and I think the condition is non-24, that people who are falling out of cycle with a circadian rhythm. So is it using a hormone or some other kind of something to replicate a system in the body to get them back in a 24-hour cycle?
Yes, we can. So light is the most powerful time cue, and if you don't have light, very little else can really substitute for that. We found about 20 years ago now that timed melatonin could, if you take a melatonin pill at the same time every day, you could resynchronize the clocks of some blind people. It doesn't work for everybody, but we do find that the majority would synchronize to melatonin. And then more recently, that led to clinical trials of a drug called Hetlioz, which is a melatonin agonist, that was recently approved by the FDA that does the same type of thing. It's a melatonin-like drug that resets the clock if you take it every 24 hours. And so there are very few things that reset the clock except light. Melatonin and melatonin agonists appear to. But unfortunately, things like meal times, exercise, having very strong social cues, they're very weak time cues, unfortunately. We really have evolved to be most sensitive to that daily light-dark cycle. It really is a key environmental time cue to keep our clocks in sync.
Well, I have to say, I found really impactful the image you had of the astronaut doing the spacewalk with the boots on backwards. That was really, really interesting. How do we prepare astronauts to all be synchronized time-wise? You know, because I know that prior to a launch, we try to get them in sync with with the International Space Station and the schedule that their fellow astronauts are on. How do we get them prepared for that so that they're in cycle?
Yeah, it's quite difficult because there are certain procedures and certain requirements for the astronauts that they have to do before they launch. And so they have to be awake for a certain number of hours. They have to be eating at certain times. So there's things that happen way before launch that have to be timed appropriately. And if launch times change, which they often do, then all of those other behaviors have to change, like sleep. And so I've been working with NASA for a while now, providing plans to help astronauts before they launch get on the right schedule for the launch, which then can change. And so sometimes that's updated at the last minute. And so we have to use light to reset their clocks or have them avoid light to help them not reset their clocks in the wrong way. We give them advice on when to take melatonin to help reset them, how to use caffeine, how to nap at the right time. And so we, with the medical operations team, provide plans to the astronauts to help them reset. We also do that though for jet lag. So as astronauts are traveling across the globe to Moscow and Cologne and Tokyo for training, we give them jet lag plans so that they can hit the ground running during training. And we do the same sort of thing for mission control for the flight directors who are working often unusual shifts and night shifts to keep in touch with station. And so all of the principles that we've learned in the lab are being applied here on Earth and then in space. It's the same thing when we change people's schedules on the space station, for example, in preparation for a docking of another craft. And so we're using these exact same things, whether you're a shift worker on Earth or a crew member in space.
Oh, that is absolutely fascinating. Well, it was very interesting, Hanya, to look at the design that your colleagues came up with for habitat on Mars. And I know that it's an aspiration to have some type of long-term presence on Mars. We know Mars is very, very far away, and with current technology, the shortest trip is around 8 months to get there. We know there are lots of challenges that still have to be resolved before we send humans to Mars. And in fact, we had a previous Thought Leader series on human mutation on Mars, discussing how we may evolve, especially for their, and procreate and have people for many generations. So the habitats that your colleagues had looked at, did it take into account the, it sounded like it did the light cycles. Were they thinking of keeping people on a Earth 24-hour circadian rhythm, or was it adaptive to the 24-hour plus of 40 minutes or so that Steve had talked about as a day on Mars?
Yeah, and also Steve is right. I think because we're still trying to figure out how to do that, if we should keep it on Earth time or the 24-hour, 40-minute time, thinking about, maybe dividing up that. This is really basic, honestly, dividing up the 40 minutes into night and day. But we still don't know exactly how. I think we're waiting for more papers and scientific responses coming out on how it's better for it to be, really, especially because also it took us hundreds of generations to adapt to our current situation. And so it's not something that overnight we can just become Martians and adapt to a day-night cycle on Mars. However, I do understand, and correct me if I'm wrong, I do know that on a normal time, our circadian time is actually closer to the Martian 24-hour and 40-minute. But we're still waiting to really understand that to make a final decision.
Well, I'm curious what all of your thoughts are in regard to the moon, because, you know, NASA's priority right now is the Artemis program, and that's returning astronauts to the moon, but again, for long duration and establishing some kind of long-term presence on the South Pole. Currently, it's a preferred site, and having Gateway as a way to shuttle astronauts to this orbiting platform. Is the light a consideration at the South Pole, because it's very dark, as I understand it, in that part of the moon, and so you're not going to have a lot of natural light. So, what are some of the conversations around how to create an environment where astronauts can be there for a period of time, probably 6 months or longer, and still be productive?
So that's actually interesting. The South Pole specifically, because it's dark, there's been conversation so far on keeping the Earth cycle over there. This helps to keep communication with Earth simpler, and also everyone's lives a little simpler in that situation. But I'm actually curious to hear if Steve has any insight on that. If you know anyone at NASA who's been specifically looking at that, and if there's been any papers, research.
Yeah, so this is something we've talked about with my colleague, George Brainard, who's my principal investigator on the space station studies. We've had some conversations about future space habitats, including the moon. And the challenge on the moon is a little bit like the Antarctic winter. And so, there might be very little natural light and really no day-night cycle for long periods of time. And so then you have to generate your own. And so it would make sense to generate an Earth day with a 24-hour light dark cycle. But that's not as easy as people think. And in fact, there's good evidence for that in some of the Mars isolation studies. And so there was one, which I'm sure people have heard of, which was the Mars 520-day mission. Now, that was a 520-day isolation mission where people lived, a crew of 6 lived together without leaving their facility for a long time. But in fact, they kept on an Earth day in that mission. So even though it was called a Mars mission, in fact, they didn't live on a Martian day, they lived on an Earth day. And in fact, it was quite hard for them to do that. One of the crew members had a free running rhythm and couldn't remain entrained to the 24-hour day. And then another of the 6 crew members had a 24-hour rhythm, but was very shifted. And so they were sleeping and waking at the wrong time of day compared to the other crew. And so even in something that sounds simple, I'm just going to give you an Earth day and you stick to it, a third of that crew couldn't do it. And in fact, on another shorter mission, 105-day mission, it was similar. And so we really have to think carefully about what light we're providing in order to keep people on the 24-hour day. And of course, energy becomes an issue. And so how do we have enough energy to generate the light? So we need to make sure that we get the biggest bang for our buck out of the light, which means having those blue wavelengths in the light. And so the right light source, the right intensity, the right timing, these are things which have to be ground tested before we take them up into space. And that's what we did with the new LED lighting on the space station. But we need to go through that same process again for the moon, for an asteroid, for Mars. Light really is important to get right before we get there.
Well, related to that, Robert, I wanted to ask your thoughts on, I know that we've benefited tremendously from Hubble and seeing these amazing images of space once you get outside of Earth's atmosphere. And of course, with James Webb, we'll be even farther from Earth. But could there be a benefit from having some type of observatory on the moon that enable us to observe or look out into space?
Well, you certainly gain a lot by moving your telescope out of the Earth's atmosphere, regardless of where you go, right? Hubble is in low Earth orbit, so it was maintainable by the space shuttle while that was possible. The Spitzer telescope that I've actually done most of my work on, we kicked that off in its own orbit around the sun. So it's been drifting further and further from the Earth year after year in its mission. And this buys you the ability to break up your observing cycle, not have to lose light through the Earth's atmosphere, which actually is very good at filtering out most of the electromagnetic spectrum that isn't in the radio or in the visible light part. So, having a telescope on the moon buys you some of that that luxury that you don't have to look through the Earth's atmosphere. And potentially, if there's a base there, then you have So, for instance, Spitzer was a telescope that was launched in its own orbit around the sun. It was inaccessible to the shuttle from day one. So it is a facility that had to work and work correctly for its over 16-year mission without the benefit of a single servicing mission. It performed flawlessly, but that takes a lot of careful engineering. If you can actually go to the telescope and do a repair if something breaks down, or if someone has a new instrument and you want to expand the capability, you gain so much by having direct physical access to it. So the idea of having a telescope at a place that you actually have humans living and operating, much like we have telescopes operate in Antarctica that benefit from servicing from people who are living and working down there during the summer and during the winter. There's definitely advantages to that. I think one area that would particularly benefit from being on the moon actually is in radio astronomy, because radio telescopes look at the longest wavelengths of light out there, and it turns out that radio is actually really useful to humans for a whole bunch of things between our cell phones and our TV transmitters and HDTV, and so much of the Earth is completely filled with radio chatter. So trying to be a radio astronomer on Earth today is like trying to be, say, an optical astronomer in a telescope with 100 people walking around with flashlights and cell phones and flash photography and everything else, and you're trying to like grab data, in between all of that noise. Putting radio telescopes on the far side of the moon would basically, the moon is a huge radio block and would give you a very, very clean background to let us, listen for some of the really the faintest signals that would be possible out there. So definitely there would be significant advantages to the moon as a location for astronomical observation.
Absolutely fascinating. Well, we are coming to the end of our time. I could keep speaking to the three of you probably for another hour with other questions, because it's been absolutely a fascinating presentation. And on behalf of Space Center Houston, I want to thank you so much for joining us for Illuminating Light. And I hope that our viewers will continue to follow our three presenters today and the incredible work and research that they are doing. And I want to thank you for joining us today for this episode of the Thought Leader series at Space Center Houston. And again, my heartfelt thanks to our panelists for joining us today.
Thank you.
It's been a pleasure.
Thank you.